Welcome all. So we have Abdus Samad here from VIT Vellore, who's a AI lab researcher as well. And today he'll present DenseNet. Over to you, Abdus.
Hi guys, I'm Abdus Samad. I joined here as AI intern and I'm doing PhD in VIT Vellore. Okay, so today we are going to discuss this DenseNet. So you might have heard BGGNet, GoogleNet, AlexNet. So we have today something as DenseNet. Okay, so I try to make it this topic as simple and as basic as possible. I normally I use board and PPT, but today we don't have whiteboard. So I'll try to make this as simple as possible. So quick question to everybody that all of you guys are familiar with CNNs, right? So just say hi and something in the chat window. You guys able to hear me, right? Just say something. I mean, this is my first webinar, so maybe no response. Yeah. Okay. Okay. Thank you. Thank you. Okay. So let's start with today's topic. Okay. So let's go back to 1990s. We have Linet 5, right? So it has 5 layers. So we are not considering here, I mean, excluding cooling layers, only convolution layers. So Linet have 5 layers, correct? LXNet have 8 layers. VGGNet have, I mean, it has different flavors with 16 layers and 19 layers also, right? And then we have GoogleNet. So all these, I mean, LXNet, VGGNet, and GoogleNet were the state-of-the-art models. So all these are the winners of ImageNet competition. You might be aware of that, right? So then we have HiveNet and ResNet, and these two networks have more than 100 layers. So even ResNet have different flavors with 52, 101, and I don't remember 152, I think, right? So, but as we are moving forward and in this technology of CNN, we are increasing the depth of CNN model, correct? And we have this ResNet with more than 100 layers, correct? But we have this problem with increasing depth. What is the problem? What is the problem with increasing depth? The problem is vanishing gradient problem, correct? So if someone doesn't know what is vanishing gradient problem, so this is the point that vanishing and exploding gradient means when you train a very deep network, the derivatives, the slope can go very big or very small. And just because of this, training gets difficult. So what to do to avoid this problem? Different authors came up with different solutions. So let's see what are all the solutions to handle this problem. Okay, so yeah, so we have different approaches to handle this vanishing gradient problem. So how ResNet and HiveNet handle this situation? I mean, not this situation, this problem. So they bypass the signal from one layer to a upper layer. I mean, maybe the next layer via identity function. We will see of short recap of ResNet also, so that it will create a proper base for DenseNet. Okay, you will easily understand uh, DenseNet concept. We just need a small recap and a small base of ResNet. We will see in upcoming slides. And we have this another paper called stochastic depth. So what does it do is uh, it randomly drops some layers from the ResNet architecture. So that I did not study this paper, but when I was going through uh, this problem, what are all the different approaches to handle this vanishing gradient problem? So I came across this stochastic depth. So I have to read this paper, but in short, what this does is it randomly drops some layers from the CNN model. I don't know how they are implementing it, but this is one of the approach to handle gradient vanishing gradient problem. Okay, so till now we have seen two ways to handle vanishing gradient. One is the resonate, like they bypass the signal, uh, okay, with identity function connection, and the another one is stochastic depth. What they are doing, they are randomly dropping some layers from the CNN model. And what CNN model they are using? They are using ResNet model. Okay, so let's move to next slide. Okay, so these are all different approaches, but they are very varying in network topology. Okay, and even the training procedure is something different. But one thing they are sharing, one thing is common, what they are sharing is they create short paths from early layers to later layers. I don't know about this stochastic there. It doesn't match with this definition, but when I was reading the paper of DenseNet, they mentioned this, that even stochastic depth is using short paths. I have to read that. I'll read maybe in next webinar or AI lab. I'll cover this paper also. It seems very interesting to me that how it is dropping CNN layers, convolutional layers. We will see that in coming, maybe in next seminar when I'll get chance. Okay, so okay, let's move to next slide. Okay, yeah. So how ResNet is handling this? Okay, this we have input layer, and the next layer is, suppose input layer is called as L, and the L1 layer, we are passing this with convolution operations, and maybe I don't know, with some non-linearity function ReLU, right? And again to L2 layer, okay, L plus 2 layer. Suppose in case this L2, this L plus 2 layers weight getting decreased, maybe they are not activating because of you may say that L2 regularization or weight decay. It may be what do you call, weights might not be sorry, feature maps might not be activating because of this L2 layer and sorry, L2 regularization and weight decay. So how this is handling is, we are passing this input X directly to the output of L plus 2 layer. Okay, you can see that we are adding it, we are summing this up. Okay, and then we are applying the ReLU function. So again, if it is suppose what do you call, deactivated, or maybe mm, not activated, not, I can't say deactivate, not much activated, uh, because of this identity function, identity connection, it will get again activate. So we can add stacks of layers in this way. So this will allow you to train much deeper network. Okay, Okay, so till now, does anybody have any doubt? You can ask in the question window if you have any doubt till now. Okay. Anybody else? Abdulaziz says no. Go on. Okay. Okay. Let's move to next slide. Okay. Okay, now let's cover this topic of DenseNet. Okay, so this got the Best Paper Award in 2017 CVPR Computer Vision and Pattern Recognition IEEE conference. Okay, and these are authors Gao Hong and I don't know how to pronounce these names, but these are the authors, and this was the collective research of them. Okay, so what we will cover today, we will cover dense block, what is dense block, and we'll see the architecture, whole architecture of DenseNet, and we will cover code demo also of this DenseNet. Okay. Oh, we have seen basic connectivity in LXNet and BGGNet and LANet. What they do is the the input goes through many convolution operations. Just simply it goes through many convolution operations, right? We just saw ResNet connectivity, right? So identity mapping is proposed to promote gradient propagation. Yeah, we just saw that identity connection is there from prior layer, previous layer to upper layer. Okay, so that is how they are handling vanishing gradient problem. Okay, that is one connectivity. One more connectivity is there which I did not mention in the slide. uh, I have explained in inception network, Google net. Okay, so there we have parallel convolutions going on with 3 by 3 convolution and 5 by 5, and there was one more 1 by 1 convolution also, and there was also pooling layer, correct? So that was parallel connections, okay, which I did not mention in the slide. Now the next connectivity which they proposed here is dense connectivity. Okay, this connectivity is called as dense connectivity. So each layer obtains additional inputs from all the previous layers. Okay, all the previous layers gives the input to the upcoming, in other words, upcoming layer, correct, and passes its own feature maps to all the subsequent layers. Okay, uh, let's move to next slide. Now this is a simple block of this is simple dense block, and DenseNet is made up of so many dense blocks. DenseNet is made up of so many dense blocks. So let's understand what is dense block. So this is input. We call this as x0, and just consider this as feature maps. Okay, these are feature maps. We call this as x0. These are feature maps. We call this as x1 and x2 and x3 and x4. Okay, and we have I mean different layers of h1, h2, h3, h4. We will see what is h1, h2, h3, h4 in upcoming slide. Right? So what we are understanding from this slide is x1, sorry, x0 is passed to h2, x0 is passed to h3 also, x0 is passed to h4 also, x0 is passed to transition layer also. So we will see transition layer, what is transition layer in upcoming slide again. Okay, so I have used this brown color. You can count that the next layers, coming layers are, I mean, what do you call? X0 has four upper layers. That is X1, X2, X3, X4. And we have four connections to upper layers, correct? X1 has three upper layers, X2, X3, X4. And we have three connections. You can see in the green color, correct? This one, and this one, and this one. We have three connections from X1 to its upper layer because three upper layers are there to X1. Similarly, X2 have these two connections because two upper layers are there. X3 has only one upper layer, that's why only one connection to upper layer. Okay, so this X3 is with aqua color, and this X2 is orange color, X1 is with green color. Okay, so till now, if you have any doubt with dense block, ask me. Otherwise, you will not understand mm, the upcoming slides. If you have any doubt, please ask me right now.
Yeah, could you repeat quickly this dense block again? So you have these feature maps, hidden layers
Yeah,
between them. I missed the part. What are these arrows going? These are skip connections.
these
Yeah,
the
yeah,
round. I mean the curve.
correct.
i- i- uh, yeah, you can say just ignore this skip part. You can say this is connection. We are passing these feature maps, X0 feature maps to H2, H3 and H4 and transition layer. We are passing these connections are like we are passing these features to upper layers. Similarly, X1 has suppose say four feature maps, and we are passing these four feature maps to H3, H4 and transition layer. Got it?
So this is different than two neural networks, two neural layers which are fully connected to each other.
Yeah. This is not a fully connected layer. We are just simply passing these whole features, whole feature block, whole feature volume to S3. We are passing whole features.
So it's going straight also, no? So it is fully connected as well as skip connection.
This is not fully connected. I mean, this is non-linearity. You can say, you can consider H2 as ReLU. We are passing this X1 to H2 also, and we are passing X1 to H3, H4 and transition there. Yeah, we have two connections.
No, I didn't
Got it?
understand difference from ResNet. ResNet also has a similar skip connection, which is added later on. There's a plus addition happens.
Correct,
It is
correct. So in case of ResNet, we are adding it, we are summing up it. Okay.
correct.
Here, I'll explain in the next slide. You will understand it more clearly. Okay. Let's have a look to answer your question. Suppose we have X0, X1, X2, and X3 feature maps. Okay. Are you getting this,
Yeah,
Vivek?
keep going. Keep going.
Yeah.
Yeah, yeah.
Okay. So suppose we are handling this H4. Okay, H4. How H4 is working. Okay. So we have H4. H4 is a bunch of batch normalization, ReLU, and convolution with 3 by 3. Okay. So we have all these previous what do you call feature maps, and we are applying H4 and we are getting X4. Okay. Now what we are doing, we have these feature maps, right? Previously we have these feature maps. X1 gets passed to H4, sorry, X4. Again, this is X0, correct? The last, the first features.
That's
Okay.
correct. We got it. Yeah, yeah.
Yeah, this is X1, this is X2, this is X3. Okay. Now, after applying H4 on these feature maps, we are getting X4, and now we will concatenate these features in this way. Did you get it now?
Yeah, yeah.
Now we are concatenating it. We are not summing it up. We are just concatenating it.
Oh,
Okay.
oh, okay, okay.
Okay. So we will have all these feature maps here also.
Right.
Okay. Okay. Got it.
It is
So
extremely dense, very, very dense. Too many parameters to train, right?
yeah, correct. So we will see how they are handling it and how they are reducing these number of features. I mean, sorry, number of parameters. How they are reducing it. So if you compare this with ResNet, DenseNet has very less number of parameters to learn. We will see it how they are what do you call reducing it. We will see it. Okay. Before that, you got it. This right?
Yeah, basically, instead of having stochastic neural layers, you are adding all previous layers. You are
Correct. All
concatenating
previous,
all previous layers to any
yeah,
current layer.
correct. All feature maps of previous layers. Yeah, correct.
So it is maintaining full memory of entire network from beginning.
Uh, yeah, correct. Yeah, we will see it. I'll tell
Okay,
you how they are reducing number of number of parameters.
okay.
Let me just
Yeah,
questions were there. So how will the model learn if all layers are connected to each other? It will overfit the model. Abdul, so we have different features, right? Gradient descent will be there, right? So you will understand this in coming slides. I think. I mean, yeah, you all will be some in confused state. Just give me some time, and then you can ask me questions. Okay. Let's see the Anupam's question. What is the difference between feature map after H1 and X1? Okay, Anupam, H1 is non-linearity. I just see H1 or H4, whatever. H4 is a combination of batch normalization, ReLU, and convolution. Okay, so just consider this as let's see. Can't use the pen. Yeah. So suppose we have x1 here and then h2 will be there. Okay. And h2 is a combination of bn and relu and con. Okay. So it will produce x3. Sorry, x2, not x3, x2. After x1, we have h2. H2 is a combination of these bn, ReLU, and convolution. And that's how it will produce x2. Let's see. Okay. Uh, Anupam, did you get it? See what are all these. Just 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 remember we have one parameter k which is called as growth rate. That means when we apply H1 on feature maps, it will create only these many feature maps. Only these many outputs it will create. So if K is 12, H1 will produce 12 feature maps. So here we have K equals to 4 and H1 is producing 4 feature maps. Okay. Now X0 has 6 feature maps. X0 is passing through H1, that is bunch of non-linearity, convolution, and batch normalization. Okay, so x0 has 6 feature maps. When it will pass through h1, it will produce k feature maps, that is 4. Now again, x1 will pass. Now x1 will be having, x1 will be now h2. See h2 here. Okay, now 4 feature maps will be going there, and at the same time x0 is also going there to h2. Now it will have x0 and x1. How many feature maps in total? 6 plus 4. Now 6 plus 4 is 10. 10 feature maps are going through H2, and again it will create only K feature maps, that is 4. Now this is again 4, and we have here x0, this is brown color with brown color, x1 with green color, and x2. Okay, now x0 have 6 feature maps, x1 have 4 feature maps, x2 has 4 feature maps. Okay, now if you concatenate x0, x1, x2, how many it will be? 14, correct? 6 plus 4 plus 4. Again h3 will produce 4 feature maps. So this is growth rate. So whenever you will concatenate the previous feature maps, it will apply convolution, ReLU and batch normalization, and it will generate only 4 feature maps. Okay, only 4 feature maps. So this was the explanation which I just these are the points which I just explained you, like uh, H is a combination of batch normalization, value, and convolution. H1 receives 6 channels from X0, correct? H1 will produce K channels, K feature maps. This is 4. And X1 will generate 10. After concatenation, it will generate 4. But after concatenation with X0, make it 4 feature maps plus previous channels. You are getting it? Did you get it? Okay, let's move on. So let's see. Yeah, there will not be max pooling between x0 and x1. There will not be max pooling. Okay, and yeah, so this compression is happening because of we have limited number of filters. We are just restricting ourselves with growth limit, that is 4. Here we have 4. It can be anything. I mean, like you can set it to 12, you can set it to 40, you can set k as 24 also. We have restricted ourselves just for an explanation. I have taken the example of 4. Okay, so if the number of filters are 4, then number of volumes will be less, correct? Number of volumes will also be 4. So if these all the feature maps are going through only 4 filters, then output will be having only 4 feature maps. Okay, so I hope everybody get this clear. Okay, still if anyone has doubt, let me know. Okay, let's
Hello.
yeah.
Yeah, Abdus, what is the intuition of?
Vivek, I'm not able to hear you. I mean, like, it's not clear. Your voice is not clear. What is intuition? Yeah, so why we are limiting this? If if we will have increasing number of feature volumes, if this suppose this x0 has six number of six feature maps, okay, and normally what happens is in every CNN model, if you see number of feature maps are getting increased, okay. Why we are restricting ourselves here is because if we are go on concatenating each and every feature volume, it will be huge, so what is the intuition is x4 will have the intelligence of x3, x2, x1, x0 also, and the feature volumes is also less. x4 will be having intelligence of x3, x2, x1 and x0, right? x4 will operate on x3, x2, x1 and x0, and it will generate x4. So x4 is having all the intelligence from x3, x2, x1 and x0. You got it, Vivek? Okay, let's move. Yeah. So this was the explanation in this is the explanation in sentences. So total number of channels will be input, x0 is input, correct? X0 is input plus k growth rate, k into current layer, L is current layer. So L in upcoming slides also, L is number of layers. Here we are denoting L as current layer minus 1. So here, suppose X2 is having 40 channels. How X0 has uh, 6 channels, correct? And we have growth rate as 4, and C and plus it will be 2, sorry, 6 plus 4 into 2, it will give you 14, correct? By this formula, you don't have to remember this. This is just to explain. And H4 is having 18 channels. Transition layer at the end. At the end we have transition layer, correct? At the end we will be having 22 channels. And number of connections. See, number of connections. Okay, let's look at the number of connections. We have 4 connection here. We have 3 connection here. Now total is 7. Okay, we have 2 connection here is here. Now total is 9. We have one more here. Total is 10. But we have connections in between also, correct? So this is one. We will consider this as 1. Okay, this is 1. This is 1. This is 1. This is 1. And this is 1. So 10 plus 5. Okay, 10 plus 5. We have total number of 15 connections. Okay, so this is just to explain. This was mentioned in the paper, that's why I am explaining it, but this is not that important about number of channels and number of connections. Okay, just I explained this because it was mentioned in the paper. Let's move further. Okay, so suppose we are generating x4 has 4 feature maps. Okay, now x0 was the dimension of x0 has the dimension of 28 by 28 by 6 channels, right? X0 is having 6 channels here, 1 2 3 4 5 6, correct? So x0 is having 6 channels here. X1 is having again 4 channels. So these are the previous concatenated layer which are going through this nonlinearity H4, okay, and now it will create 4 feature maps. Got it? It will create 4 feature maps. Why 4? Because we have growth rate as 4. Growth rate as 4 means we have only 4 filters, and it will be having how many? It will be having intelligence of x0, x1, x2, and x3. Correct? Now, in the next layer, in the next operation, what will happen? This x0, x1, X2 and X3, these are all feature maps. These feature maps will get concatenated here. We got X4 here, and then afterwards, all the previous feature maps will get concatenated. Correct? I have mentioned here after concatenation. Okay. Now this layer, this non-linearity, non-linearity in the sense that I'm using this as in a very short form. Actually, I have to use batch normalization, ReLU, and convolution. So this layer, this this H1, H2, H3, and H4, this is called as composite layer. Okay, everybody get it? If you have any questions, please ask me. Okay, I am moving further. Okay, now we have seen resonate is adding adding is and here in dense block we are using concatenation. We are just concatenating these feature maps behind the current generated feature maps. Okay, so we are using concatenation, and yeah, each layer receiving collective knowledge from the all previous layers. Okay, and this is how, I mean, I don't know, I I was successful in explaining thinner and compact sense to you guys. Still, if you have any doubt, please let me know. So see, here we are restricting our network with just 4 feature maps, newly generated 4 feature maps. That's how we are restricting it. That's how it is known as thinner and compact.
Abdus,
Yeah,
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 so it becomes multi-scale feature map after the X4, right? Because those feature maps are at different scale. You can concat them because they are of same dimension, but they are at different scale because they were at different stages. So it becomes a multi-scale feature map, right? A
multi.
multi.
I mean, I'm
The
not
agree
getting.
because X0 was at a different scale, X1 was a different scale.
No,
These.
scale. So yeah, yeah. Thank you for asking me this question. So we are using here same padding. Okay, so dimensions will not get changed. Every feature map will have this the same dimension. Only yeah, 28 by 28. Height and width is same. 28 by 28. 28 by 28. 28 by 28. Did I answer your question?
No, I was talking about resolution of the feature map. So it is a they are at different resolutions, X0 to X4. So it is 28 by 28, but the resolution density may be different. Uh,
Well, these are the feature maps, right? This is the input volume. This can be anything. I mean, the volume size, the depth can be anything. I mean, it can be 12, it can be 48, and it will generate new feature maps with only growth rate. With
mhm.
okay, did I
Yeah,
answer your question?
yeah. I think it's okay. So in case of images, initially it's low-level features like edges, contrast, colors. Later on, it's high-level features like face, nose, mouth. So
Correct.
we'll
Okay,
end up
okay.
kind of we'll end up concatenating them, which is okay, I guess, because it's just a mathematical matrix. So we'll concat them. That's fine.
Okay. Yeah. I think I did not answer your question, but if you think it's fine, let me move on. Okay.
Yeah, yeah.
So, okay. Yeah. This I explained. Yeah. So now I have explained this composite layer and concatenation and everything. Now we have this something as transition layer. So what is transition layer? So this was all about one dense block. This is only one dense block. Okay. We have DenseNet with multiple dense blocks. Okay. We have DenseNet with multiple dense blocks. So and between those dense blocks we have transition layer. Okay, so here I can explain you in more clarity that this is one dense block, this is one dense block. Okay, so this is the dense net with three dense blocks. Okay, and between these two dense blocks we have two layers, right? Convolution and pooling, the two layers, and these two layers are called as transition layer. Okay, so transition layer is made up of, here we will do one batch normalization, then one by one convolution, and then pooling. Okay, so one by one convolution will not reduce number of feature maps. Oh, okay, it may reduce, but it will not reduce height and width, and this pooling will reduce height and width. Okay, okay, so this is one by one convolution. Before that batch normalization will happen, and pooling. Okay, pooling is 2 by 2. Okay, so this is called as transition layers, this is transition layers, this is transition layers. Okay, so between two dense blocks we have one transition layer, between two dense blocks we have one transition. Okay, yeah, so feature extraction, this is going in this direction. Okay, this is the arrow mark, this is going in this direction. So input, then convolution, then dense block, again transition layer, dense block. Okay, yeah. Now we have something one more, bottleneck layer. So if you have studied inception network, inception what do you call inception V1, inception V2, in that model we had something called as bottleneck layer. Okay, so suppose let's uh, take an example again with this network. Okay, just suppose we have something like k value, I mean growth rate value is 16, suppose, just in case 16. Okay, so x1 will be having 16 feature maps, x2 will be having 16 feature maps, x3 will be having 16 feature maps, again x4 will be having 16 feature maps. And how many feature maps will be there at transition layer? 16 into 4 plus x0. Correct? So the feature maps at transition layer is very big. I'll say it is very low. If you take an example of 16, instead just take an example of 64. 64 into 64 into 64, 64 into, sorry, 64 into 4 plus x0 feature maps. So it will be huge number of feature maps. So what to do to reduce those feature maps? So something we have here is bottleneck layer to reduce number of feature maps. So how it is working? Let's take this diagram as an example. So one by one convolution will help you to reduce number of feature maps. Correct? So sorry, it should be till here. It should be, suppose it should be when it should be till here. Just ignore these feature maps. So what I meant to draw here is one by one convolution is reducing number of feature maps. Okay, so one by one convolution will reduce number of feature maps. And how many feature maps we want here is 4 into number of growth rate. Okay, so here they have fixed number of feature maps after one by one convolution. This is bottleneck layer. So they have used this bottleneck layer in 1 second in this in these models, DenseNet 201 and DenseNet 169, because their feature maps were getting increased. They have not used this bottleneck layer in a basic model. The basic model they have used for CFAR and SVHN. These are the dataset names. So for CFAR and SVHN datasets, they have different architecture, and for imaginary dataset, they have different architectures. They have four architectures simultaneously. So we will look into that afterwards. Let's see this. So everybody got this how it is reducing one by one convolution. If you have any doubt, I would suggest you that you should read Inception Network, or I think Network in Network (NIN) is another paper. So they have mentioned one by one convolution there also, how they are reducing feature maps. If somebody did not get it, I would suggest them to read these two papers, Inception and Network in Network, because if I have to explain this, how they are reducing it, again, it will take half an hour, I think. So I'll move on. So this is the bottleneck layer, and as I said, they are having different models for different data sets. Okay, so when in a what do you call in DenseNet, if they are using bottleneck layer, they are calling it DenseNet B. Okay, so DenseNet B means they are using bottleneck layer. Okay, yeah, let's go on. So they have used something to compress the feature maps also. So I don't know. I mean, they could have used same technique for one by one convolution. Maybe for one by one convolution, number of parameters to be learned is getting increased. That's why they have used something compression. So eh, they are using a parameter something theta. Okay, so the value of theta is between 0 and 1. So theta is called as compression factor. Okay, and when theta is the same, I mean theta is the 1, the number of feature maps will be same. Okay, if theta is less than 1, say theta is 0.5, the number of feature maps will get half. Got it? Will get half, because we have n feature maps, and it will generate theta m feature maps. So if theta value is 1 by 2, okay, 1 by 2 or 0.5, it will generate half of the feature maps. Okay, so if they are using compression technique in DenseNet, they are calling this as DenseNet C. And if they are using bottleneck layer and compression together, they are calling this as DenseNet BC. Okay, so let me see some questions here. Uh, yeah, DenseNet is a state of the art paper. I'll discuss the results also. Okay, so you will get the idea how it is much better than ResNet. Okay. Okay, concatenate all the feature map, and we are not using, we utilize feature maps, and after that reducing by bottleneck. I did not get it. So if number of feature maps are getting increased, say let's take an example of this model here. Where is the structure? Okay. So in DenseNet 201, they are using K as 32. In DenseNet 161, they are using K as 48. I mean 48 feature maps here, and here 32 feature maps. Okay, but the depth is 201. 201 layers are there, and growth rate is 32. Just imagine how many feature maps will be there at the end. 32 plus 32 plus 32, that means 32 into 201 feature maps will be there at the end. So to restrict number of feature maps, see, if the number of feature maps are getting increase and increase, we will have that many filters. You're getting it? That many number of parameters we have to learn. So it will be huge. It will be huge. Okay. So to reduce those, we are using bottleneck and we are using compression technique. Okay. So I think it is clear. And we have one more question. Mm, so we have a question that compression and max pooling is not the same. See, we are in pooling we choose max amount, uh, say 2 by 2, I mean 4 values. Okay, if we are using pooling layer 2 by 2, 2 by 2 pooling layer, so we have 4 values. Okay, we will choose max value among 4 values. Okay, that is pooling. And here compression, see number of feature maps. Okay, number of feature maps we have n in the previous layer, and we are deciding, we are restricting ourselves uh, by using theta value. So here in the paper they have used theta is equals to 0.5. Okay, so they want to reduce number of feature maps. See, number of feature maps, suppose number of feature maps are what do you call 128. Just in case I'm taking an example, 128 feature maps are there. I mean m equals to 128, or theta value is 0.5, so it will give you value of 64, correct? So in the next layer we are restricting ourselves to generate only 64 feature maps. Okay, so I think it is clear now. Still, if anyone has doubt, let me know. Mm, see, I mean, pooling will reduce your dimensions, and compression will reduce the number of feature maps. It will not reduce the dimension. It will reduce the number of feature maps, and pooling will reduce the dimension. I mean height and width. Okay. Yeah. Yeah. So okay. Still, if anyone has doubt, please let me know. How it's okay. Let's go. So I think everybody is clear with bottleneck layer, transition layer, composite layer, and compression technique. Okay. So if they are using, just a small recap, if they are using bottleneck layer, they call this as DenseNet B. If they are using compression technique, they call this as DenseNet C. And if they are using both the things, they call this as DenseNet BC. Okay. Now let's discuss the architecture of DenseNet. So as I mentioned earlier also, mm, that they have created different architectures for different data sets. So they have different architecture for CFAR and SVHN, and they have different architecture for ImageNet dataset. Okay, one second. Yeah, one by one convolution also reduces number of feature maps. Correct. So that's what they are doing with here with bottleneck layer. So they are reducing number of feature maps. But what happens is with one by one convolution also you have uh, learnable parameters. So again, I think the authors might have used this compression technique because they doesn't want to increase number of learnable parameters. Otherwise, they could have used again one by one convolution here also. But yeah, with one by one learnable parameters is also there. So might be. It's totally my understanding why they have come up with this compression technique. Uh, they did not mention why these two different techniques they have used. This is my analogy. Okay, let's move further. So about architecture. So we were discussing about architecture, correct? So for CFAR and for SVHN, they have different architecture, and for this ImageNet dataset, they have different architecture. Okay. So on the CFAR and SVHN datasets, the DenseNets used in experiments have three dense blocks, and each have an equal number of layers. Layers means layers mean these are the layers. Okay, they might have restricted themselves as maybe for 5 layers and only three dense blocks. So we have three dense blocks for SVHN and CFAR data sets. Okay. Now for ImageNet datasets, ImageNet dataset they have some really, I mean, I think it's mm, very complex architecture. Let's see what they have. So suppose growth rate K is 32, and let's discuss this DenseNet 121. Okay, so first they have 7 by 7 convolution. They are really reducing it to uh, they are really reducing the dimension and width and height because they are using stride and they are using again 7 by 7 convolution, and again they have this max pooling of 3 by 3, and again the stride of 2. So see, they have dense block, first dense block. Okay, and what do you call these 6 layers, and again in the next dense block they have 12 layers, again in the another dense block, so third dense block. Okay, so here for imaginary data set with 121 layer they have 4 dense blocks with 16 layers, oh sorry, 6 layers, 12 layers, 24 layers and 16 layers. At the end they have average pooling. Here also in CFAR and SVHN, I think yeah, most probably they have used global average pooling, and at the end softmax layer with 1,000 categories. So we have 1,000 categories of images in ImageNet dataset. Okay. Yeah, so we have growth rate for every DenseNet as 32. Just for 161, DenseNet 161, we have growth rate as 48. Mm, yeah, so between every convolution, what they are applying batch normalization, ratio, and convolution. Here in CFAR and SVHN also, between every two convolution layer, they are applying Bayes normalization, radio nonlinearity, and convolution. And convolution led to only with 3 by 3. Here they are using bottleneck layers. Why? How? I mean, how do we know they are using bottleneck layers? Because they are using one by one convolution here. Okay. Okay. So let's move to another slide. Okay. So as I mentioned earlier, if you go on increasing number of layers, it will have vanishing gradient problem. Okay. So but here in DenseNet, we have the intelligence from all the previous layers in a dense block. Okay. So we have a strong gradient flow. Correct. This is how they are solving vanishing gradient problem. Correct. We have seen the connectivity in case of ResNet also, right? So they are using identity mappings. Here we have DenseNet connections. Okay, so that's how they are solving strong gradient flow. One second, guys. Still, if you have any doubt, ask me. Okay, let's go further.
Yeah, Abdus.
Yeah.
So, how did vanishing gradient improve by this scheme?
So, okay, let me show you the PPT of the authors. Okay, 1 second.
Because you are preserving the intelligence across the board, and that is why the gradient flow is better.
Yeah, I'll show you. I'll show you. 1 second. 1 second. Let me show you the PPT of authors. Okay. See, so we have connection from every layer to upcoming layer, correct? So while back propagation, again, we have connection from the last layer to the first layer. Is this diagram helping you?
So even the back prop is through all the layers.
Correct, correct. So we have connections, right? So in the backend, TensorFlow or whatever platform you are using in the backend, they will calculate these connections.
Okay, got it.
Okay. Okay. So yeah, yeah. So let's see how it is more efficient in terms of parameters. So in case of ResNet, the number of channels will be, suppose C is the number of channels. Okay, so in case of ResNet, it will get multiplicated, correct? And here in case of DenseNet, L is the number of layers, correct? And we have growth rate as K. So at the end, we will be having number of layers into growth rate square. I mean K into K. Okay. I mean, I would have explained you here. I'm not feasible with this pen. Otherwise, I could have explained this calculation how they are calculating it. Okay, maybe in the next webinar if I get a chance to explain there in Bangalore. Okay, so here the value of K is very less. See, the value of L is also less. We have limited number of layers. We have restricted ourselves with a growth rate of say 12 or 32, whatever. But here we have no restrictions over channel, right? So it will be huge and it will be very less. Now the next advantage of this DenseNet is, see, in the ResNet we have correlated features. We are adding previous layer's feature map, right? So we have correlated features there in ResNet. But in the case of DenseNet, we have more diversified features, correct? So here we have diverse features, correct? Here we have more diverse features. In case of ResNet, we have correlated features. So if we have more diverse features, new generated feature maps will be having more intelligence. Okay, so this is how it is helping to learn the patterns. Okay, now let's come to the results. Okay, let me explain what this plus is. So this plus means they are using data augmentation techniques. So without plus means they have not used data augmentation. Okay, wherever you see plus, that means they have used data augmentation techniques, and they have mentioned number of techniques what they have used in these architectures. Okay, so I did not mention here because I find that that is not important. We just crop or we just flip it horizontal something. I think everybody knows what is data augmentation. Okay, so let's see. This C10 is CFAR 10 and this C100 is CFAR 100. These two are the different data sets, and we have SVHN data set here. Okay, so we have total of 3 data sets, and C10 plus C100 plus is with data augmentation techniques. Okay, now let's see, let's compare this with only with ResNet. Okay, now ResNet with a depth of 110, and let's compare this with DenseNet with 100. Now check the number of parameters here with the ResNet. Okay, 1.7 million, and here we have 0.8 million parameters with the growth rate of 12. Okay, now here we have depth number of layers as 250, and I don't know with what to compare. 250 is too much. Okay, so just think with 110 and 100. So it has very less number of parameters, 0.8, and almost I think half of the parameters of ResNet, and even the it is it is 110 and it is 100. Now these bold values are what they have mentioned in the paper. Sorry, blue values are state of the art results. Okay, for C for 100 and C for 10 with plus, I mean with augmentation and without augmentation. And here you can see growth rate with K. Okay, so this is the results of C for 10 and C for 100 and plus SVHL. Okay, let's see their different models. As I explained, DenseNet, plain DenseNet. Okay, sorry. This is DenseNet with bottleneck compression technique. Okay, this is DenseNet without bottleneck and without compression. I mean, this is plain DenseNet. This aqua color, this light green color without compression. Oh, sorry, without bottleneck. It means they are using compression, and here they are not using bottleneck layer, but they are using compression, and here they are using everything with blue line. Okay, so you can see the results here, right? Test errors and number of parameters. Okay, even though the number of parameters here without bottleneck and without compression is less, but at the same time the test error is more. here with bottleneck and compression, but yeah, it raises the doubt that how it is increasing the number of parameters here. If anybody can answer me this, I don't know. I mean, just now I got this doubt that with bottleneck layer and with compression, the number of parameters should be less. I don't know if anybody can help me out with this.
No, I
Let's go
think they
on.
are saying that number of parameters are a tad more, but test error has gone down remarkably.
Yeah,
So
yeah, yeah, Vivek.
error is less
The number of
by
parameters are
increasing
more. Yeah, error is
slightly
less,
more.
but they are using, yeah, but they are using compression and bottleneck. So I think with compression and bottleneck, the number of parameters should get reduced, right? We are reducing number of parameters, right? Sorry, number of channels with compression and bottleneck. So how the number of parameters?
Compression.
I think you got my question, right? My
Yeah,
doubt.
I got it, but I think it's not too bad compare too far in number of parameters are close.
Yeah,
They
it's
are
not
very
too.
close.
Yeah, yeah.
See,
It's
the
all.
four lines are tracking each other. They are pretty close. The main
Yeah.
point is that the error rate is falling.
Correct.
So error rate is marginally better with the blue line, but in terms of number of parameters, they are not too far. They are close.
They are close. I have to go through their implementation. Yeah, let's see. Let's see. Let's
See, you cannot always assume bottleneck and compression will reduce the parameters.
okay.
So you cannot assume that because there are other things which get probably added.
Hmm.
So number of parameters doesn't change that much, but error goes down. Error goes better.
Yeah, yeah, might be. Yeah. Okay, so here you have all the results of you know they are comparing their implementation with ResNet. So you can see here the difference between test error, right? So ResNet is with red line and DenseNet with the blue line. Here again, they have mentioned test error with with number of layers, 100 layers and 1001 layers. How many parameters are training loss and right? Okay. So it's pretty good model, I think, according to me. If you see that they are, half of the parameters, they are getting a better result than ResNet.
So if
With
this is the
ResNet.
case, why don't we see DenseNet more frequently used? Every time we see ResNet used, maybe the scientists have just sort of defaulted to ResNet as a backbone network for most other algorithms, and DenseNet has not found resonance with scientists.
Maybe, I don't know. I mean, like you might have seen different varieties of ResNet. ResNet with inception, ResNet with I don't know. I mean, like there are different ResNet with stochastic depth and wide residual network. There are a lot of you know varieties of ResNet. I did not see DenseNet with different varieties. Maybe because DenseNet came into picture 27, maybe at the end of 27 or 2017 year, and ResNet came, I think, in 2015 or 2016. Maybe that might be the reason.
Right, right.
Okay.
There's a question here.
Yeah. 25 million parameters. 25 million. Yeah, so we have 190 number of layers, 190, and we have number of features as, sorry, the growth rate as 40. Maybe because of this, if I don't know. Yeah, if you compare straightforward with 100 and 110, it's almost half. And here also in the picture, in a graph, right, number of parameters you can see. Okay, number of parameters here we have more, but what is this DenseNet? How many layers they have used? They did not, I think, one second, let me check with the paper.
Yes, a balancing act between number of parameters and test accuracy. So there is a trade-off.
Maybe, yeah, yeah. One second, one second. Did they mention here how many interesting curves? Okay, I don't know. Again, I think, yeah, that is the question. Yeah, I got it. I have to read it again, I think. I don't know. Yeah, but this is true that it's 25 million parameters. Maybe because of this growth rate. I don't know. I did not see the whole architecture of this 190 layers. I have to go through it. I don't think so. It's possible to go through 190 layers of architecture. Let's see. Okay, let's move on with ImageNet. They have this results. Okay, yeah. So let's go through the demo of DenseNet. Okay, one second. Here the question. And DenseNet was the state of the art. Yeah, they stopped the accuracy based evaluation from 2017. Oh, is it? Okay. And yeah, yeah, which you, yeah, correct. Maybe because of, yeah, I told you that maybe because of growth rate, it might be increasing number of parameters. Okay, so yeah, I was running this afternoon. This let's. Okay. Can you guys be able to see the code, or should I increase the font size?
No, it's visible.
Okay, okay. So see, I did not implement this DenseNet on CFAR or SVHN or ImageNet. I have implemented this on for MNIST dataset. Okay. So let's see. We have the architecture of 28 by 28. I just modified it instead of 32. So we have CFAR 10 with 32 by 32 by 3 dimension. So I used MNIST with the dimension 28 by 28 because this is one because it is grayscale. Okay. So yeah, the important thing here is we will just look at the, so here I'm normalizing it, okay, means and standard deviations of the image, and then subtracting mean and dividing it by a standard deviation to normalize, okay, to normalize the input image. And here we are converting this into categorical data. I mean, what do you call it as one hot encoding? I think, yeah, one hot encoding will be better term for this. So instead of 1, 2, 3, 4, the labels of images, we are converting it to one hot encoders. Again, we are reshaping the test images. Okay. So this is not important. I think you guys know all this basic terms and pre-processing, normalizing and all. So let's go directly to the dense block. Okay, so here all are all the, I'm importing all the libraries. Okay, now see, we have DenseNet. Okay, we have DenseNet here. We have dense block size here. We have layers in block, right? We have classes. We have classes as 10. Okay, and we have growth rate, that is K. We have filters. Okay, now let's see. So we are applying convolution operation on input image with the same padding. Okay, and we are initializing the kernel weights here. Okay, we are using 24 filters. So I just used it randomly because they did not mention clearly when I was implementing this model. They did not mention clearly how many what do you call number of feature maps they are using at the first. Here they did not mention how many number of feature maps they are using. So that's why I just started with some random value, that growth rate into 2. Okay, growth rate, we have growth rate as 12. Okay, number of classes 10, dense block size is 3. That means we have 3 dense blocks, and in each dense block we have 4 layers. Okay, we are calling here DenseNet. Now DenseNet function is here. Okay, so this is the first convolution operation we are applying on the input image. That is the shape of 28 by 28 by 1. Now we are applying batch normalization on that. Okay, this is X. We are applying batch normalization, and again we are applying ReLU, and then max pooling. Now this is, see, this is the network. Just look at the network. Okay, we have first convolution here, which we did here. Okay, we did here, right? And then we applied batch normalization and non-linearity activation, right? ReLU. And then we have used max pool. Now the next is we have dense blocks. Okay, we have dense blocks. First dense block, then one transition layer, then another dense block, and one more transition layer, another dense block. And here we don't have transition layer. Did you observe this? We don't have here transition layer. See, transition layer is combination of convolution and pooling. Correct? Convolution, that too one by one convolution. Okay, so we don't have here transition layer. Okay, so after using this dense block, we don't have transition layer. Okay, so okay, so okay, dense block size is 3. Correct? We have 3 dense blocks minus 1. So the loop will continue for 2 times. Okay, so we have one dense block, we have one transition layer then. Okay, now this is dense block, this is dense block function. Okay, now let's go to dense block function. Now see, I told you we have 4 layers in every dense block. Correct? See here, we have 4 layers in every dense block. Okay, so it will run for 4 times. It will apply convolution operation. Okay. Again, this is calling one more function. Okay, this is function. Where is the function? Here. So what is happening in one convolution layer? I told you, you can say this as H1, H2, H3, H4. Correct? So this is non-linearity. We are applying batch normalization, activation, and convolution. This I use just purposely. They did not mention in the paper to use dropout on convolution, and just wanted to see. Even I don't know how it works with convolution. I know we use dropout with dense layers, near the output layer. I mean, whole we use flattened layers, right? We use flattened neurons. So there we use dropout. I don't know how it works on convolution. If someone can help me with this, just wanted to check if it helps me or not. And even they did not mention in the paper to use dropout with SVHN and CFAR network. So just wanted to see it. Okay, you can ignore this also. So yeah, with every convolution we have three operations: batch normalization, activation, and convolution operation with the same padding. This is how they are maintaining the height and width inside a dense block. They are using same pattern, correct? So this is one layer. Then the previous layer gets concatenated with the output of this. We are using concatenation. Okay. Now it will go on in a loop. You're getting this? Okay. It will go on in a loop for 4 times. Layer in a block. Layer in a block is 4, correct? So it will go on 4 times and it will generate 4 layers in a dense block. Okay. Now after dense block, see where is the dense? Yeah. See, we have called dense block here. Now we have after that transition block. Transition layer, correct? The transition layer is a combination of 1 by 1 convolution and pooling layer, correct? 2 by 2 pool. This is 1 by 1 convolution, correct? Before that we are applying batch normalization and activation. So after dense block we have one transition layer. Now again it will again run. Now it will create the next dense block, I mean second dense block, and then again the second transition layer. Now till now we have created one dense block, one transition layer, again one transition layer. Okay. Now just come out of the loop. Why? Because we have two statements in a loop. We did not want to we don't want to create transition layer. We have only two transition layers, correct? This is one transition layer and this is one transition layer. We don't have third transition layer, but we have third dense block. Okay. So we have third dense block here. We are calling third dense block here. And then we are using average pooling. Okay. But before that, we are applying batch normalization and redo. And then after dense global average pooling, we are using softmax, that is output layer. This is the fully connected layer, right? Dense layer. Okay. We are using softmax layer. Okay. So I think this is not a complex. I think everybody can make it. And why don't you guys create dense block DenseNet for CFAR 10? Just try at home today with the shape of 32 by 32 by 3, but number of channels will be 3, right? CFAR is a color images. CFAR has color images, correct? So I think this is clear. Okay. So now let's look at the summary. Let's look at the network architecture. Okay. So at the first we have 28 by 28 by 1. This is the input. Okay. We are applying convolution. Okay. We had growth rate into 2 number of filters, right? We had growth rate of 12. 12 into 2 is 24. Okay. So 24 features we are using here. Correct. We are using 24 features. So 24 batch normalization, activation, and then again and again. Okay. Now again, see here, look here. Here it is again 12. Here again it is 12. How it is 12? Because we are creating this one, this we are creating k channels. We are creating k channels. Here k value was 4, but here we have k value as 12. So here one more layer we are creating, and then we are concatenating it. Here you can see it. Correct? We had earlier 24 feature maps. Now, after concatenating 12 feature maps with 24, we will get 36 feature maps. Correct? So it will go on concatenate. Okay? Again and again. Okay? Okay, so this is it, guys. I hope you guys are clear with this. If you have still any doubt, please let me know. So yes, we can. You have done average pooling, not max pooling. Reason. Uh, 1 second. 1 second. We have used. Where is the architecture? Okay, 1 second. So to answer that question, they have used global average pooling here. So I have implemented, just by looking at the architecture. So again, I have to go through the paper why they have used global average pooling, why not max pooling. So maybe I think they have mentioned in the paper, but I missed that. Okay. So one more thing, normalize. Hmm, maybe they have mentioned in the paper that we need to apply batch normalization after every layer, right? They have used in the paper, they have mentioned in the paper that H4 I mean before applying convolution, they have used batch normalization and ReLU in every text block. They have used it. Okay. Okay. So still, if anyone has doubt, please let me know. Okay, guys, this is it from my side. Hope you have understood. Still, if you have any doubt, you can ask me offline. Okay. Over to you, Vivek.